Hi, in this video we're going to derive the step response of an RC circuit. Now let me swap my camera out so we can focus on the content. Okay, now before we derive the step response, I want to see if we can gain a little intuition about what actually goes on when we apply a unit step function to the RC circuit. So here's our RC circuit. Our input is going to be u of t, step function. Here's our resistor, and here's our capacitor. Now what is u of t? It looks something like this. Before t equals 0, it's 0. And then at t equals 0, it jumps up to 1 volt, and then it stays at 1. So, at t equals 0 minus, which is instantaneously before t equals 0, Vn of t is 0 volts. So Vn of t is 0 volts. And the capacitor is uncharged. Now at t equals 0 plus, which is instantaneously after t equals 0, Vn of t becomes a DC voltage of 1 volt, DC. There's no charge on the capacitor, so the voltage across the capacitor is 0 volts. Vc equals 0 volts, which means that the entire 1 volt has to go across the resistor, so Vi equals 1 volts, which means that we're going to get an initial current flowing through the circuit of I0 equals 1 volt over I, and this comes from Ohm's law. As t increases, what happens is that the capacitor keeps charging. So as you get more charge on the capacitor plates, the voltage across the capacitor increases. So Vc increases, which means that the voltage across the resistor decreases, so Vi decreases, and by Ohm's law this corresponds to a decrease in current. So I of t decreases. And at t equals infinity, the capacitor is fully charged. It's fully charged. So the current is 0. I equals 0 amps. And the voltage across the capacitor, because if there's 0 amps of current, then the voltage across the resistor is 0, which means that all the 1 volt DC voltage goes across the capacitor. So Vc equals 1 volt, and of course Vi equals 0 volts. In the previous video, we mentioned that the role of the resistor is that the resistor affects the rate at which the capacitor charges and discharges. And it turns out that this will produce a characteristic time dependence that turns out to be exponential. So we expect the voltage across the capacitor to look something like this. Here's our time axis. Here's our V out of t, which I think I forgot to draw it here. V out of t is taken across the capacitor. Here's V out of t. So initially we're gonna the rate of increase in the voltage across the capacitor is going to be high, and then as t increases, the rate is slowly going to decrease as it asymptotically approaches the DC voltage of 1 volt. Now let's see if we can quantify this. For t is greater than 0, I'm going to apply KVL around the loop of the RC circuit. So we're going to have minus 1 plus I of t times I plus V out of t equals 0. Now remember, the current flowing through the capacitor I of t equals C times dV out of t dt. So we have IC dV out of t dt plus V out of t equals 1. So this is a first order constant coefficient linear differential equation. How can we solve this? Well, we can apply separation of variables, because I'm going to move V out of t to this side and then divide both sides by RC, which gives us dV out of t dt equals 1 over RC times 1 minus V out of t. Now this only depends on V out, so we can multiply both sides by 1 over 1 minus V out. So we'll get dV out over 1 minus V out equals dt over RC. Now I can integrate both sides. This becomes minus ln of 1 minus v out of t. And this becomes t over ic plus some constant k. Now I'm going to multiply both sides by minus 1, and I'm going to take the exponential of both sides, which will give us 1 minus v out of t equals e to the minus t over ic plus k, which is e to the minus t over ic minus k, which is e to the minus k, e to the minus t over ic, and e to the minus k is just another constant. So I'm going to call this a. And now if I move v out of t to this side and move this expression to the other side, I'm left with v out of t equals 1 minus a e to the minus t over ic. Now, remember, we assumed that at t equals 0 minus, the capacitor was uncharged. So v out of t is 0. So if we apply that initial condition, v out of 0 minus equals 1 minus a e to the 0, which is 1, which equals 1 minus a, which equals 0 volts, assuming that the capacitor was initially uncharged. This is equivalent to saying that a equals 1. The step response of the RC circuit when the capacitor is uncharged at t equals 0 is v out of t equals 1 minus e to the minus t over ic times u of t for all t. And this is the step response of the RC circuit.